Hello and welcome everyone. In this podcast we're going to talk about how we study human heredity. Now, one of the problems with studying human heredity is that humans are not model organisms for various reasons, not to mention social reasons and ethical reasons. But aside from that, there's things you can't do with humans that you can do with our typical model organisms. We can't have controlled matings in humans, or at the very least we shouldn't have controlled matings. We have an incredibly long generation time, and when we do have progeny, we usually don't have large numbers of progeny. Something like a Drosophila that has thousands of eggs at a time, that's a lot of progeny. However, understanding human diseases, human heredity, and how diseases are inherited from one generation to the next is very important. So some things that we can use to our advantage is that we can study model organisms. Since we share a common ancestor with these model organisms, and we share many of the same genes, what we learn in a model organism can tell us a lot about us as humans. Apart from inheritance, we understand things like human physiology. And anatomy. And even biochemistry. We understand these things very well in humans. We can use this to our advantage once we start understanding the function of genes. Throughout generations, many of us have good family records. We may be able to tell a geneticist how far back a certain trait goes. Or we might say, at least on our mother's side, we know this trait goes back X number of generations. Those are useful pieces of information for a geneticist. But these next three are where we're going to spend our time talking about in this podcast. Using some of the information here, particularly the family records and our knowledge of human physiology, anatomy, and biochemistry, we can build pedigrees. Having a strong pedigree can tell us not only about our past and about our previous generations, but it can help us make predictions about what the next generations, our children, how they will be affected. We can also use twin studies. By studying monozygotic and dizygotic twins, we can understand a great deal about human heredity. And finally, in a similar way that we use twin studies, we can use adoption studies. So as I said before, we're going to focus primarily on these last three here, pedigrees, twin studies, and adoption studies, to understand human heredity. Okay, before we get started with talking about pedigrees, I want to talk about the difference between a multifactorial trait and a polygenic. Not really say compare them, but to define each of these, because it's kind of important. Multifactorial traits are traits that are influenced by genes, and usually more than one gene, plus the environment. Polygenic traits are influenced by greater than one gene, so more than one gene. Most traits fall into these categories. In fact, most traits are multifactorial. Very few traits don't have an environmental effect and a genetic effect. As we go through these pedigrees, recognize that everything is not just the genetics of it, that the environment also plays a role, and you have to kind of balance these two things. So who uses a pedigree? Well, certainly genetic counselors use pedigrees. These pedigrees will help a genetic counselor work with their patients to tell them the probabilities of certain traits appearing later on in their lives, or how certain traits might be passed on to the next generation. And certainly genetic researchers use them, particularly human genetic researchers, but not exclusively human. In addition, pedigrees are really important in understanding certain kind of animal and plant breeding. So it's very important in agriculture. So let's now go on and look at some pedigree symbols. And let's just draw a pedigree. So what I've drawn here, this would be our first generation. And we usually put a Roman numeral 1 there. Squares are symbols for males, and circles are symbols for female. This line between the two symbols means that these are the parents of the next generation. And to show that next generation, what we do is we draw a line. And in this case here, we can see this couple had 3 children, 2 males and 1 female. This is our second generation. Now we can make note of certain traits. For instance, maybe this male was a heterozygote. To show a heterozygote, sometimes we just draw a line through it, or sometimes we'll color in half of it. Both are fine. Let's make both mom and dad a heterozygote. So these are both heterozygotes for this particular condition. And let's say this son has the condition. So in this case here, this child is fully affected by it. They're not heterozygotes. We might also call these heterozygotes carriers. These 2 children are unaffected. So nothing shaded in, unaffected, fully shaded in, fully affected. And these 2 don't have the condition, but they are carriers of it. Let's say she has a child with this guy over here. And let's say they had, their second child was a girl, and their third child was a boy. But their 4th child was spontaneously aborted. Now sometimes we don't see these on pedigrees, but when we do, typically they're shown as a diamond, because often we don't know the gender of a spontaneously aborted child. If you do know the gender, you could make a small circle or a small square. But the diamond just means that the gender is not known. Now we could say over here that this person died. We don't know how they died. We don't know if they died of the trait or what reason. But if they're dead, we draw a line through it, like so. Okay, let's have this son having children with this lady here. And let's say they had twins. This is how we show twins. From the same line, we draw an arrow like that. And if they're non-identical or dizygotic twins, we would draw it like this. We're going to make them both sons, but they're dizygotic, non-identical. If they're identical or monozygotic, we connect them like such. We connect the triangle. I think these are our basic symbols that we really need to know. One last thing though, and this is important. Let's say this pedigree was built because this son here, the identical twin of this one, the children of these parents, the grandchildren of these parents here. And if they are the ones that started this, initiated it, we put a P by there. And this P stands for proband. Just for a record of knowing how we built this pedigree. It was because of this person. One last symbol that I didn't show is just to show how we would indicate adoption on a pedigree. In adoption, you would have your biological parents here. They're not part of the pedigree because they don't share any of the same genetic background. And let's say they had another child here, this child here, who was adopted. We would put brackets around this child like that and draw a line like so to indicate that this child shares genetic material with this family but in an environment with this family. This is very helpful in understanding how certain traits are passed on from one generation to the next. Okay, let's erase this and start looking at some specific things we look for in pedigrees. We're going to look at examples of autosomal, recessive traits. We'll look at examples of autosomal dominant traits. We will look at some examples of Xlinked recessive traits. We'll also look at some examples of Xlinked dominant traits. We'll look at examples of Ylinked traits. Ylinked traits are neither recessive or dominant. They're just traits. And not in this podcast, but in a future podcast that we might cover it here, we'll see, would be mitochondrial traits. Okay, so let's begin by looking at some autosomal recessive traits. Let's just draw this pedigree first, and then we'll analyze it. Okay, so here's our pedigree with our 4 generations. Who we have affected here is this person. I'm going to just make it a different color so it's a little easier to see. They don't have to be different colors. That's how we're going to do this one. And you might have noticed something different on this pedigree that I haven't talked about in the sample I showed. And that is showing this double line here. When we have a double line here, what that means is that this relationship between these two that had these children is what we call a consanguous relationship. And that means when people who are related to each other have children. And these two happen to be first cousins. For this pedigree here, and I should have indicated up here what we're talking about, this is going to be an autosomal recessive trait. Now, as I was saying before I wrote that there is, in order to have an autosomal recessive trait, you don't have to have people in the same family having children. But it does increase the chances, because usually we all have a lot of recessive traits within certain families, and they have an increased chance of passing it on to our children if we have children within our family. This is why, apart from many reasons, it's not a good idea to have children between first cousins. As we can see, it is evident as when we look at monarchies that have a lot of inter-family marriages, when we see cases like of hemophilia in the royal line. Okay, so let's get back to this pedigree here. So let's write down some common characteristics that are associated with autosomal recessive traits. First of all, we can see that they are typically equally represented between the genders. So no gender bias. Requires both alleles to be mutated. 3, can, and I stress the word can, skip generations. You can see in this pedigree it does skip a generation. This generation is not affected. It's important to point out though that it doesn't have to skip a generation. It just means it can. These recessive alleles can remain hidden within multiple generations for several generations in a row. Or they can pop up periodically. Like for instance, if this person was a carrier and this was a carrier, they could have a child with it, with the trait. So it doesn't have to skip a generation, which is a common misconception. The fourth one I'm going to put here, we have an increased incidence of progeny from related parents. So let's also list some examples of autosomal traits, autosomal recessive traits. Albinism is one, which we've talked about before. Tay-Sachs, which we briefly talked about, and something like PKU. That would be another example. So in class and on exams, you'll get pieces of a pedigree like you see here, and you'll have to make the best possible guess between which pedigree it is. So think about these characteristics, memorize them, and then you'll be able to make your best guess possible. Another thing I want to tell you about pedigrees, which I didn't mention before, I told you that when somebody is a carrier, we draw it halfway in. Now, sometimes it's not indicated, because when you build a pedigree, you don't always know that somebody's a carrier. So when you're looking at one of these and have to answer for a quiz or an exam, the fact that we don't indicate that these two people are carriers doesn't mean they're not carriers. It just means we don't know if they're carriers. From this data here, we suspect they are carriers. But when this pedigree was made, we didn't know they were carriers, so it's not always indicated. So don't let that trip you up. Okay, now let's look at an autosomal dominant trait. Alright, so if you don't have this written down, go ahead and hit pause and catch up. Right now what I want to do is I want to indicate all the affected people here. She's affected, this son's affected, this daughter's affected, this son is affected, and she's affected. Okay, so what I want to do now, before we walk through this in detail, let's talk about some of the traits associated with these autodominant traits, or I should say the characteristics associated with autosomal dominant traits. And as we go through these, we'll point them out in the pedigree. So again, no gender bias. If you count these up, let's see, we have 1 male, 2 males, 3 males, 4 males, and females we have 1, 2, 3, 4, 5. It's close enough. On an exam, if there is a gender bias is supposed to be assumed by you taking the exam, I'll make it clear that there's a lot more women versus men, or a lot more men versus women who have that trait we're looking at. Does not skip generations. You can see here, this person had it, and she passed it on to some of her children. He had it, he passed it on. She had it, she passed it on. She doesn't have to pass it on, but she can. Just like we see here, this individual didn't get it, and he was from these two parents, but he didn't get it. And this is the key here. He didn't have it, and you will never see it in his line again, unless he marries somebody with it. But he won't pass it down. None of his children will have it. None of their children will have it. This is a dead end road for that trait. But if a person has it, then there's a 50% chance the next generation will have it. Every affected person has at least one affected parent. These two are affected, their parents are affected. These two are affected, their parent is affected. The probability of passing it on to the child is equal to 50%. This is linked to, doesn't skip a generation, but let's go and just say it anyhow. Unaffected parents do not pass it on. And for this one here, let's go ahead and write their genotypes. This person here has to be, and we're just going to use big A, little a. This person has to be big A, little a. They have the dominant mutation, big A, and the recessive allele that's not the mutation. This person here would be little a, big A, little a, little a, little a. This person would be big A, little a. All you need is this one big A mutation, this dominant mutation, that's why it's capitalized, and the person will have it. The unaffected people will be little a, little a. Let's write some examples here. We'll write our examples right here. Huntington disease is probably one of the best examples. Another one is hypercholesterolemia. Okay, let's go ahead and erase this and look at an Xlinked recessive trait. So let's go ahead and draw the pedigree. This person here is a carrier. This person's a carrier. This person is fully affected. Fully affected. Carrier. These two are fully affected. All right, a few things to look at as you're looking at this pedigree. We're already told it's Xlinked recessive, but let's look at some of the characteristics of an Xlinked recessive trait to see if this makes sense. We will see more males affected. And that's what we see here. We have 1 male here, 2 males, 3, 4 males. No females are affected. And the reason for that is this is an X-linked trait. So she up here, she's XX. We know she's a carrier. One of them is mutated. It's recessive, so she's going to be fine because she has this backup copy. She has children. This means 50% of her sons will have this trait because she's going to give one of these X's to 50% of her kids, the other X to the other 50%. And so in this case, this child is X minus, he got the mutation from mom, he gets Y from dad. This daughter here, she received this mutation, the X minus one from mom, but she got the X without the mutation from dad. Here, she passed this X mutation on to this son. Dad gave him the Y, but since he, just like this male up here, only has one copy of the X chromosome, he's going to express the trait. This son here, he got this one. Lucky day for him. And Y from dad. And it looks like she got this here with no mutations. So the reason for this is because men are what we call hemizygous, meaning they only have one X chromosome. None of an affected male's sons will have the trait. Because he's only going to give the Y chromosome to his sons. He can't give the X chromosome to his son. So here we see this affected male here. He can give this X to his daughter and she'll be a carrier, but he cannot give it to his sons. So none of his sons will have the trait. And all of his daughters will be carriers. Could have the trait if mom gives it to him as well, but we assume not. Linked to this, affected males have to get the mutated X from mom. I'm out of room here, so I'm going to write the rest up here. 4. It can skip generations. We don't see it here in this particular pedigree. Well, I take that back. We see it here with this group. They don't have the trait, but in the next generation they do. So it can, but it doesn't have to. It just can. Affected female. So we don't have an affected female in this pedigree, but if we saw it, we would see this characteristic here. Affected females pass trait to all sons. Some examples we'll write over here. Hemophilia. Color blindness is a classic example. And muscular dystrophy is another one. All right, let's erase this and let's next look at an X-linked dominant trait. So an X-linked dominant trait. All right, let's go ahead and fill in who has the trait. He has a trait here. This daughter has it. This daughter and this daughter. This daughter has the trait. She has the trait. I'm sorry, he has the trait and he has the trait. These are males. Let's make sure that's clear. These are squares. She has the trait and so does he. And let's give her the trait too. Okay. As we look at this pedigree, let's go ahead and mention some of its characteristics. It can occur in either gender, as we can see here, but an increased chance in females. And this is a little bit more difficult to explain than with the X-linked recessive trait. And sometimes we don't know why this is the case, but often the reason is that if you have an XX female where she has this dominant mutation, and so you get the effect of that dominant mutation. She also has this one over here, which is still functional, so it kind of relieves some of the pressure that this negative one's having, and she survives. Whereas the male, when he has it, he only has that one. And often is the case with these dominant X-linked traits, he dies, but you don't ever see him in the pedigree because usually it's lethal and they don't survive to birth. So if you did see him, they might appear as like small sections or small symbols. So that's one of the reasons that on a pedigree, often X-linked dominant traits, you see more females affected than males. It's a little misleading because often males are also equally affected. It's just that, or even maybe more so, it's just that we don't see them. But we still say on a pedigree, because that's what we're looking at here, that more females are affected. Again, we mentioned before, and maybe we can add some here. And remember, these are going to be written as small triangles. I mean diamonds, small diamonds. And these mean spontaneous abortions. And so this might actually be a little bit more reflective by putting some of these on here. Wouldn't have to have them, because sometimes as these are being constructed, these are unknown, that there were spontaneous abortions. Hello. As I was editing this video, I realized I made it sound as if all X-linked dominant traits have this degree of lethality to them, and that's not the case. Some do and some don't. In the cases where there is a degree of lethality with them, you will notice that many of the males don't make it to birth, and for that reason you would see more females surviving, and so they would be represented on the pedigree in more numbers. Now, in traits that are not linked to lethality or even health, you would still see males and females present, but the traits in the males would be more prominent because they only have that one X chromosome, whereas the females have two X chromosomes. So their traits might still be less severe or less phenotypically noticeable. I thought I should clear that up before we proceeded. Okay, let's go on to the next characteristic of X-linked dominant traits. Cannot skip generations. Just like with the autosomal dominant traits, X-linked dominant traits cannot skip a generation. For instance, over here on the left, this son did not get the trait. Since he doesn't have the trait, he can't pass it on to his children. It's gone from this side of the family. Over here, once it's in this side of the family, it tends to stay in that side of the family. These two people here, this son and daughter, when they have children, they won't have the trait and they won't pass it on. Affected men pass it on to all daughters. Affected women pass it on to 50% of her children. Now, if she's homozygous, she's going to pass it on to all of them. But it's very, very rare to have a homozygous X-linked dominant trait in women. Can happen, but it's rare. Linked to these, but we'll say it because to kind of tie it all together, affected males will always have an affected mother. Because you had to get that mutated X from somebody. We'll write some more here. Affected female has one affected parent. Doesn't matter which one, but one of them has to be affected because she gets an X from both parents. And the last thing I want to say, and it's linked to this over here, affected males have an increase by an up arrow. I'm showing that increased trait. Whatever the trait is, it's going to be more expressed or more evident in the males. And that goes back to this idea here that even though it's dominant in females, the unmutated X will help balance that to some extent. But the male doesn't have it. So some examples we'll write up here. Really running out of room. Let's see, a vitamin D resistant rickets. That's all we have for the X-linked dominant traits. And now let's move on to our Y-linked traits. And there's very few of these, but they're out there. So Y-linked traits. And so let's, once again, start building a pedigree. Alright, let's go ahead and fill in who has the trait. The original father has the trait. All of his kids have it, all of his sons, I should say, have a trait. And this couple here, again, all their sons have a trait. Both of his sons have the trait, but none of his daughters do. And the son here has the trait. Alright, so I'm sure as you noticed here, a key characteristic here is only males affected. Because only males have the Y chromosome. So once he has it, all of his sons are going to have it. The sons then, when they have children, all of their sons will have it. and so forth. This son had it from grandfather up here, and now all of his sons have it. A daughter will never have it. Affected males pass it on to all their sons. And an affected male, in the same sense, also has to have an affected father. Even though it's not, well, it does not skip generations. Include things like hairy ears and retinitis pigmentosa. And also, I'll put this one too, fertility. But you'll never see fertility on a pedigree, because if this male has infertility because of a mutation on his Y chromosome, he's not going to have children, so it would never be here. But certainly fertility is a Y-linked trait. So in solving a pedigree, a few things you should do. The first thing you want to ask is it dominant or recessive? And the easiest way to determine this is, does it skip a generation? On an exam, if I want it to be recessive and you to get the idea that it's recessive, I'm going to have a pedigree where it's showing it's skipping a generation. So if it skips a generation, you know it's got to be recessive. If it skips a generation, that's a good sign that heterozygotes exist. Two unaffected parents having an affected child is a sign that they are both heterozygotes and that it's recessive. Now, next question is it Xlinked or autosomal? And if it's Xlinked, we know there will be a gender bias. So if there's a gender bias, then we know it's Xlinked. No gender bias, it's autosomal. So by asking these two questions, you'll be able to tell if it's dominant or recessive, if it's X-linked or autosomal. If the gender bias is only males have it, then you know it's Y-linked. So I guess I should put here or Y-linked. Then look at the pedigree and fill in the genotypes. And then ask yourself, does it make sense? After looking at the genotypes you put in, does it show the kind of prediction, the kind of inheritance pattern that you have predicted, with it being dominant or recessive or X-linked, autosomal, or Y-linked? Okay, I'm going to end this podcast now. Originally I was going to put the twin studies and adoption studies on the same podcast, but it's running a little long for a single podcast, so I'm going to have two parts to this particular topic. On the next one, we'll finish this up talking about twin studies and adoption studies, and then have a single summary for both podcasts here, covering pedigrees, twin studies, and adoption studies.